want to introduce myself to anyone who's online who doesn't know me. My name is Wiley Jones, and I'm a senior at the University of Illinois studying mechanical engineering. Kind of done a little bit of dabbling in electrical engineering, getting a minor right now. And, previous work experience has been, ranging from working as a research assistant at University of Illinois, working at Cummins Power Generation, kind of on some product design stuff, and then actually spending my past summer at PwC doing tech consulting. So I've kind of been all over the place. I think if you know me, I got a wide array of interests, and so I think pretty well reflected in this. This is something that I wanted to learn about, and I kind of took a deep dive on the technology just to kind of really ingrain myself in it, kind of get integrated. Really, the big point of this kind of webinar was just for my own personal learning. So I created these slides, put these together. It's just a fun project and kind of a way to motivate myself to learn more about the technology, what's going on in the space. I think a large portion of that I can contribute to a couple of my friends, kind of shouting out to Jay Bensall and Raj Pant. They got me really interested in certain aspects of like the artificial intelligence. And from there, it was a rabbit hole and I kind of dove in. So, all right, well, I'll dive in, kind of get started, lay out a little bit of an agenda for us. So what are autonomous vehicles? We're going to go over the technology. We're going to kind of talk a little bit about my thesis, artificial intelligence plus robotics equals autonomous vehicles. We're going to kind of go into the self-driving stack a little bit as well. Like the technology stack, when you think of that for computers, there's different types of tech stacks, and the same principle applies to vehicles: sensing, processing, actuation. Those are kind of the big three. Then we'll just take a brief look at like what's up next, kind of the trends, what's going, coming in the pipeline right now. So that's it. I'm going to hit it off right now and we can kind of go in. Feel free to hold your questions kind of till the end. I'm not going to be checking the chat, so feel free to hold your questions till the end. We can try and get those answered at that time and kind of get some discussion going. All right, so what is an autonomous vehicle? Well, for this kind of sake of this discussion, we want to limit it to cars and motor transportation, maybe even trucks, but we're not going to really hit as much on that. Really what it is it's a vehicle that's capable of movement and navigation with limited or no outside instruction or intervention. And there's a spectrum, and that's something we'll kind of go into the next slide, that people have really argued over what does fully autonomous mean, how autonomous can things be in the legal sense of what they drive on the road as. And I think there's been a lot of, kind of derision and classification that people have tried to, wrangle these all different types of autonomous vehicles into. But at the core, it really is just a vehicle that's driving with limited interaction. It's capable of movement. And I think the U.S. Department of Transportation kind of described autonomy in terms of tiers. That's why you always hear tier 1, tier 2. People always are talking about like kind of the golden standard of tier 4, which is what most people think of when they think of autonomy, where the vehicle is performing all safety critical functions and monitoring the roadway with absolutely no driver input, no real control by any type of human or any type of remote person. So really what this would boil down to is allowing for unoccupied transport of vehicles. So imagining freight liners, imagining taxi cabs with no driver in the seat. And they'd be able to operate across like all range of functions like that with no one in the driver's seat. So that's kind of what people are shooting toward. Right now, you look at like, things like Tesla, it's closer to tier 2. It's got really glorified lane centering, like an adaptive cruise control. It doesn't work in all cases. It's got navigation, but it's definitely limited. And so tier 4 is kind of what people think of when they really think of full autonomy. I'm putting air quotes kind of around my words there. So the main thesis of kind of what we're looking after for the day is AI plus robotics equals AVs. So artificial intelligence being injected into the classical study of robotics and the movement of mechanical and electrical mechanical systems really enables autonomous vehicles and autonomous movement. And really the core concept that underpins my thesis there, and I think one that I share with many people, there's nothing novel about the concept that I'm kind of bringing up, is that an intelligent system that's able to take information and data and really transform that into actionable commands and input that into a mechanical system. That's really what an autonomous vehicle is. Modern machine learning techniques are absolutely skyrocketing in terms of the complexity and what they're capable of handling in terms of image classification. I mean, examples like AlphaGo, Google's board game player. There were scientists that said 10 years ago that said Go as a game won't be able to be played by machines for a century. It just kind of shows the order of magnitude of increase in this field that we've been seeing. Similarly, deep learning techniques are being applied to vehicles. They're given high volumes of data and they're being taught to drive simply in an almost borderline unsupervised fashion. And so we're seeing some really interesting things that are kind of being injected into robotics, and the intersection is becoming really, really interesting. So robotics is really a well understood field. It's had decades of research and progress. I think people have a great idea how mechanical actuators work, how a lot of the sensors work, but autonomy can't be hard coded. It must be learned. And so that's, when I say that, that means that there really isn't a possibility to kind of cover all the rules of the road. It's something that you kind of have to use your own gut judgment as a human, and you kind of putting your vehicles would have to do. They wouldn't be capable of doing that unless they learned how to drive. So kind of a forward-thinking statement. Autonomous vehicles have kind of been a scientific dream. The science involved is something that people have been working on from many different channels over the past decades. Planes have been capable of this type of autopilot self-flying feature. It's taking such a long time to hit cars though, because there really are too many possible scenarios that could occur while driving. Planes don't have a lot of roads they need to follow or a lot of things that they need to be avoiding up in the sky. And the rules for these robotic vehicles can't be hard-coded the way they can be for planes. It's much simpler. So really true autonomy and moving towards that's going to require artificial intelligence. Intelligence that resembles the human capability to decipher, understand, and encode a 3D space that changes in time, a 4D space. And with decades of advances that we've had in the artificial intelligence field from computing backgrounds, really great research institutes like CMU, Stanford, even University of Illinois, we're really nearing a time where this is becoming an actual possibility. It's something that's no longer a scientific dream. It's becoming a reality. So kind of taking a dive into the technology. I'm gonna take a break here and first drink a little drink of my water, but I'm also gonna look and see if anyone's been dropping into questions or anything. I don't think we've got anything right now, so I'm gonna head on back. Feel free to text me questions if you would like. If you have my number, maybe message me on Facebook also, and I can kind of contribute those. So kind of taking a deep dive into the technology. What we got right now is that stack that I kind of mentioned. And if you look at a lot of the lingo and a lot of the white papers that are coming out and you see things on the news about autonomous vehicles, there's way too much to handle. There's all types of verbiage. I'm sure everyone's heard the word LiDAR by now. It's become very popular as a method of sensing. And I think, we want to look under the hood and really try and see what's going on. Try and simplify a lot of these techniques and terms, because really people are using them incorrectly and in ways that maybe don't really hit the true nature of what the technology is doing. So we can take a dive in right now. Looking from the high level, what's going on in an autonomous vehicle? Well, it's what happens in almost any type of system. It takes in some type of input, it processes it, it manages it, it understands it, it learns what's going on with that input, and then it does something with that. So you have a sensing phase, a processing phase, and an actuation phase, right? And they all feed into one another. It's a loop of feedback where the sensing goes into the processing, which goes into the actuation, which then repeats and takes in a new amount of sensory input and learns what to do with that, and then continues to control itself. And so that's part of the self-guiding, right? If you look at a self-driving stack and you imagine just the regular vehicle stack, the human handles the sensing and the processing mentally. We see what's on the road. We figure out what we want to do with it. The actuation, we turn the wheel, we press the gas pedal. So now you're needing to imagine kind of where the vehicle's gonna have to make decisions. It's gonna have to have eyes, it's gonna have to have a brain, it's gonna have to have the capability to move the vehicle the way it wants, right? Once it understands what to do in its environment. So these are some of the problems that we're kind of getting into and that some of the technology is looking to answer. So what that means, kind of using the human brain, the human system as an analog again, you got a lot of sensors out there that act as the eyes and ears of the road or of the vehicle, of the autonomous vehicle. The most popular one that always people talk about nowadays is LiDAR. Basically, we'll kind of dive in, take a deep dive on LiDAR, but there's also video cameras. People are using still images, that turn into video feeds frame by frame. It's just pixels. And, there are more specific sensors then, where people are looking maybe like at a specific sensor they'll place in the car that detects red lights, or another one that detects pedestrians, something that you can't really do with maybe like sonar, where it only is able to detect metallic objects very easily. So you take all this sensory input and you imagine you have a big cluster of it in some sort of file input that's read into a processing unit that's stored on board the vehicle or over the cloud. Okay, so this sensor data is passed on. It's computed in these algorithms that we'll talk about later on. It's processed in GPUs, graphical processing units, which is the most common way of locally processing things, or over a distributed cloud network, in theory. And that's something that we'll kind of also get into. And once this sensory data is kind of wrangled and managed and understood, and the vehicle knows what it means, it turns that into a command. Then goes to the wheels, it goes to the motors, it goes to the engine, depending on if you're a gas or electric vehicle. And it then drives the car and it makes decisions. It decides, am I going to apply this much acceleration? Am I going to apply this much, of a steering angle? So it kind of feeds through and then it loops back on itself and it repeats the process until you get from point A to B, essentially. Something we're kind of overlooking here is the mapping, like, with navigation at a higher level where you have GPS points. And that kind of is a bit of a wrench in the system. That also would come in the sensory input. It would have localization where it would know where it's located, kind of in the grand scheme of things. But again, that's a little bit kind of outside the scope of what we're talking about, is the actual technology that sits in the autonomous vehicle. So like I said, we kind of have the positions of these. You can see there's cameras on here. There's electromechanical actuators, something that controls the throttle, the steering, the brake. You've got things that are like laser rangefinders, LiDAR, that sit on the vehicle that'll kind of give it those eyes. You've got controllers and computers that sit on board, maybe in the trunk or wherever. And these are what kind of the things that you would imagine to sit on board the vehicle, just kind of give you a visual of kind of what correlates to what. So kind of breaking these down now piece by piece, there's really some fascinating technology that sits at each one of them. I think sensing is one that it doesn't seem as glorious, and it's definitely not as talked about, I think, but it really is one of the most rapidly advancing aspects of the autonomous vehicle technology, and it's also something that I don't think is really fully appreciated how hard it is. So we'll kind of get into that. LiDAR, everyone talks about LiDAR. It's all over TechCrunch. Any type of outlet you see like that, you hear about some sort of new LiDAR and sensory company that's raising money. Really what LiDAR is doing is it's taking in data, reflectivity data that passes off of objects, reads it back in, generates a 3D point cloud, which you can kind of see the picture to the left. And it gives kind of like a high-res view, really. I mean, that right there, that picture, it's very clearly, evident that it's a road with trees and, all types of stuff around. You can even see the lane markings. There's kind of a color map based on like the height and the z-axis. And so it does have aspects to it that, that make it really, really ideal for certain techniques. One of the other popular ones that people are using is video cameras, just because it's simple. I mean, you can use a phone camera with great video input, very cheap, and feed still images that can be processed. That's something that a lot of companies are now turning toward, because really the sensor is one of the limiting factors in the vehicle right now. And I think people are trying to come up with clever workarounds and ways to utilize more existing technology like video cameras. And so, like we said, again, specific sensors, that's something that people are using to kind of augment the two that are above, the LiDAR and the video, because the LiDAR point cloud, you can't really tell in there what is the stop signs. You can see maybe what things you don't want to hit. And with the video cameras, maybe you can kind of see who people are, but you don't have a good idea of how to find maybe lanes, or you don't have a really good idea of looking at maybe like the stop lights, like we said, or like stop signs. So it's kind of like an augmentation, right? It's kind of filling in the gaps between those two. And there really are interesting ways that people are coming up with to use those. So deep dive on LiDAR. LiDAR, like I said, it's become a go-to. Velodyne is one of the industry leaders. There are other ones that are kind of coming up now. Basically, it sends out pulses of light, measures the time that it takes to return, and kind of computes where that point is located in space. A lot of the times these LiDARs are rotating, and so it generates a cloud. You can kind of see the rings around there. What's great about it is really visually, it's kind of sensible to see that this is a way of generating a 3D environment, representing space in real time. It's something that we can understand as humans, and it makes a ton of sense of us. It's a ton of sense to us to see the world that way, for a vehicle to see that world that way. Although there are LiDAR applications like Velodyne's that spin, a lot of research is being put into solid state LiDAR just to make it cheaper. This chip that we're looking at here that sits absolutely on like a tiny little coin is only like between $10 to $20, they're saying at this point. It's got a really short range, like 2 to 3 meters, but they're really working to try and increase the distance, increase the accuracy and precision while maintaining it as a solid state and cheap type of sensor. Things like this are really going to break the ceiling on what autonomous vehicles will be capable of. And so it'll be interesting to kind of follow this research. This came out literally 2 weeks ago, and I think it's very evident to that the landscape is rapidly changing in the sensor space. Like I said earlier, they need to fuse a lot of this together. The image in the top right is from the Google cars, kind of what they're seeing. They see vehicles, they see stop signs, they see even speed limit signs, and that's kind of maybe read in from GPS data. They kind of see the world through cameras and through LiDAR. So it's really important to take that all into account and kind of perform this sensor fusion. So it's going to be interesting to see how that kind of landscape evolves in the future, what sensors become more important than others. Moving into one of the most important topics of the night, basically the processing part of the stack. This is where, like I said, decades of research in artificial intelligence and robotics has gone into the algorithms. It's gone into the technology that actually, the hardware that really performs the processing, the muscle, right? I think I cannot overstate how important this part of it is. It's something that I think is heavily fixated on, but for a great reason. It really does represent kind of right now the state of the art of what these vehicles are capable of. People are putting massive amounts of time and money into understanding the computer vision and into understanding really how you connect some sort of muscle to an algorithm to really make sense of what data is being fed into the vehicle. So we can kind of dive into that now. Like I said, as with most types of things, the processing stack is very similar to most input-output types of systems. There are methods in which we compute by. There's a muscle that does the heavy lifting. It's CPUs, GPUs, systems on chips, large amounts of flash memory. You got to store all this information somewhere, and that's kind of like a local compute, really. It's something that's done on your computer. It's done on the computer that's in the vehicle. And then there's also this concept of distributed computation, where you have a cloud, some sort of cloud network, really powerful endpoints. Let's imagine you have access to some type of server with, clusters and clusters of, computing power. The only speed that, the only limitation on that is how fast you can communicate data between the vehicle and the distributed cloud network. So that's a really interesting concept that people are beginning to explore. Using this muscle, they really apply it to all these different types of algorithms, rule-based systems, which are the most basic that you can imagine, just kind of almost like conditional statements of the road, kind of the rules of the road. More advanced techniques like motion planning and mapping will kind of investigate SLAM, just kind of the general idea of it. And then kind of the newer, more ambiguous types of ideas coming out of artificial intelligence and machine learning and deep learning, using convolutional neural nets, using basically just any kind of deep neural net, and like an end-to-end learning that's almost agnostic to any type of model. And it's just being fed the sensory data. It's being fed potentially like IMU data. So it's maybe inertial units and measurements from a type of vehicle. It's reading the acceleration. It's reading the wheel encoding, kind of where the vehicle's at in the GPS coordinates. It's reading in even potentially things as advanced as temperatures in order to, kind of see where am I at in terms of rain or sun or shine. So it's something that's really interesting right now, kind of how these deep learning techniques are kind of getting into, wrangling this data and turning it into real commands. But the end goal of all these computational methods is to, take that muscle and take that data and put them together and really wrangle in and create some sort of output that can be actuated upon and can be acted upon. So kind of diving into the methods, really just the methods by which these computers are kind of wrangling the data. You got motion planning, kind of the old guard, kind of what people have done for decades and what people have investigated very heavily throughout the kind of the space of robotics. And then you have kind of the new guard, the people that are really working heavily in artificial intelligence, machine learning, deep learning. I think a great way to describe the emergence of a lot of the artificial technology or the artificial intelligence techniques is that there are a lot of AI researchers that are hammers looking for nails, and self-driving vehicles is a great example of that. It's a really powerful technology that's been very stubborn to kind of apply, and they're finding a really awesome application in autonomous vehicles. So kind of starting off with motion planning, we have SLAM, simultaneous localization and mapping. I pulled these kind of quotes from a CMU paper where they're talking about really the basics of robotics and SLAM. The idea is just that some type of robot, or let's imagine some type of autonomous system, some sort of vehicle, wants to know what's around it in the world. It senses that, and then it kind of generates a map via the measurements it's taking, via the sensing. And then it kind of figures out, where am I in that world? Once it understands the world, where am I relative to all the things that I understand, right? So it's relative, and it generates probabilistic models based on maps that are kind of built in prior. And then really it tries to understand where it's at, and then it repeats the system of, okay, let's resense the world. Then let's generate an understanding of where I am in it, right? And so there's a great paper that I cited below that talks about the Kalman filter being applied to this. You can kind of see the probability distributions in the picture to the right, where it shows like the likelihood that the vehicle is located in these positions. It becomes better when you apply these types of learning methods with the Kalman filter. And that's something I'm not going to dive into too heavily. It is extremely technical and something that I don't necessarily understand perfectly myself. So kind of walking through SLAM, it's a really cool technology. So the idea is that there is a robot with landmarks. It scans them, it reads in where they're at, and now wants to move, and it sees, okay, let's move to this new position, kind of marked in purple. It's going to move over there. It's going to take new measurements, okay? So it understands the world around it when it was at position 1. Now that it's moved to position 2, it kind of retakes measurements, and it understands it's changed in odometry. It makes new observations. It extracts the landmarks. It's trying to figure out where it is in the world that it's kind of understood at this point. Takes these two readings and associates them together. It matches them up and figures out, oh wait, based on my measurements that I've taken internally, and now the new measurements I've taken out in the world, I see there's actually a difference. I have some error, right? It measured incorrectly, either by the measurements it takes with its lasers or the measure it takes within itself, within its own odometry, maybe like a wheel encoder or like a GPS coordinate, right? What it does is it takes those 2 points and establishes a left and a right bound based on types of Kalman filters, maybe not a left and a right necessarily, but a probabilistic like XYZ understanding of where it's located. And it knows that within this area, it's located in some type of distribution within a probability. And it can kind of get a good idea that, yeah, I'm somewhere in the middle to this XYZ standard deviation, right? So imagine this now in 3D space. The same types of algorithms are applied to drones that actually have to move within X coordinates, Y coordinates, and up and down in the air, right? So this is kind of an idea, just a general approach to figuring out where robots are in the world when they want to move on their own, okay? So now the idea of this is that when we know where we're located in the world and we've localized ourselves, how do we figure out where we want to go? So that was kind of the movement of like, that odometry change. Once a probabilistic localization is realized, a probabilistic path can actually be generated using these things called RRTs, rapidly exploring random trees. And they're just a set of exploratory algorithms generally used in things like maze generation, all types of different stuff. But a really useful application of them is in trajectory planning. Polygon obstacles, this is kind of like technical jargon that was taken from these papers, but the idea is that it takes these obstacles, it generates a random tree, it puts that through a vehicle controller model, which is something that comes from dynamics of mechanical systems. It's basically systems mechanics that you can input some type of you can put in, some type of, I guess not necessarily a goal, but if you look at the controller down there to the bottom right, you can see that the tree is input as a possible path. It predicts the trajectory of that path based on a model and an understanding of the vehicle. Let's say you generate a tree of possible steerings and possible speeds, and it determines, based on the vehicle, where you'll end up being during those times. And then it rules out the possible ones based on what your goal is, right? And so you can kind of see the picture up there does a great job explaining it. Kind of a complicated set of algorithms. There's actually a wide array of approaches to this because the runtimes of these albums can be very, very, very difficult to wrangle. They can vary significantly in time based on the number of samples you're taking. If you're looking for high resolution types of paths with lots of polygon obstacles, you can get very, very high run times. And so this is something that people have been working very hard on for very, very, very many years. It poses a really big issue for high speeds with these vehicles when they're moving at high speeds, just because it's constantly having to provide updates to its guesses. If a new set of inputs comes into the system and the SLAM algorithm determines a new set of polygons that the RRTs have to navigate around, and this is happening on the fly, let's imagine it's 60, 70, 80 miles an hour, that's going to require some massive compute to be able to do that in time for the vehicle to respond accordingly. And so that's kind of what we run into with this, is that you don't see a lot of high-speed moving robotics like this because it is inherently difficult to wrangle from really just from a processing perspective. Cool. So artificial intelligence, machine learning, deep learning, and techniques that are being applied right now to this space, there really is a lot that's going on. This is something that I'm super excited about. People in the field are super excited about. The newly emerging methodologies are really all revolving around this because it hasn't not provided results, and so they want to explore the possibility of it providing results. I think the really two main forces that are driving the adoption of these methods, though, is that the powerful computation has become available. GPUs and then distributed cloud computing, even GPUs distributed over the cloud, not even locally, are making this far easier to do than ever. And then really open source deep learning platforms, you look at things like TensorFlow, the open source version of MATLAB, Octave, things like that are making it easier and easier for people just generally that are out there in the field wanting to explore this to really put together compelling research studies, research cases. A couple people on a team at Comma.ai were actually able to perform their own research with a team of less than 15 individuals in a way that would have taken teams at like the IBMs and NVIDIA's massive teams with very, very large resources to be able to perform these types of research studies. So it really is fascinating to see where all this is going. I'm going to give a brief explanation of kind of how this all works, especially with the purpose of kind of using it for motion planning and how it's applied to autonomous vehicles. There's a lot of acronyms. There's a lot of really, really dense verbiage, and it's something that I don't necessarily understand perfectly myself, but I'll kind of try and wade through it. What we've got here is just kind of a playground that someone set up to kind of basically understand deep learning. What it really is it takes a bunch of nodes that are inputs, and it has all these hidden layers within, and there's connections between them the way you would imagine like neurons, like a neuron and neurological setup within a brain. And they're weighted based on an input. They're nodes and edges with weights. And it essentially minimizes a cost function or an energy function or some sort of like method of determining the loss or the quality of the output. And that's kind of seen in the top right. And it just iterates evolutionarily, adversarially. There are many different techniques to how it evolves and how it decides the weights. But really what it's doing is just trying to minimize how wrong it is. And you can kind of see here that it takes a really sharp curve once it understands the path it needs to take forward in order to correctly understand the system in question, the data points in question, and its classification, basic classification. This type of classification can really be blown up into a massive scale of what you'd see for a different example of this, and what you have with this NVIDIA end-to-end learning for self-driving cars paper. They literally just took a massive amount of forward-facing video feed, so from a camera that was on the front of a car, and they trained it using deep learning techniques and convolutional neural nets against steering wheel position. And the networks were capable of extracting road features with almost no to the limited, kind of additional nudging. There was some simulation that occurred where they used it to gather more correct data in order to teach it better. But the vehicles are largely driving correctly on their own. And so that's a fascinating paper to look through and read. It kind of gives a great overview of some of the really cool applications that are going to be coming out of the deep learning space looking at autonomous vehicles. Similarly, Comma.ai, they used another type of paradigm of the deep learning to actually generate video input, or to generate new video feeds and future predicted feeds based on video input. So they took hours and hours of video feed. They created auto-encoded video that predicted frames in the future up to like 100 frames while maintaining the road features. So, imagine you're driving on the road and then you close your eyes and you try and picture in your head what the road looks like as you go. Maybe a little scary, but that's essentially what this learning simulator was doing, which is totally fascinating, and more research coming out of them probably very soon within the next couple of months. Similarly, there's groups at Facebook's AI, individuals at Facebook's AI group, as well as NYU, that are doing a lot similarly about, the auto encoding for video, and that's being applied very largely. If you can see into the future and you can guess into the future, you can wrangle that and turn that into some sort of insight for the vehicle to be able to take a path forward. So that's a really important part of this, something that, I think these types of papers here are really going to become seminal works in the space, and I think are going to be largely applied in autonomous vehicles and maybe even beyond that. Computational muscle. So the muscle that kind of underpins this, and we can kind of briefly go through this. We're kind of nearing time, and I've only got a little bit more. We've covered a lot of the good meat so far. We've got CPUs, we've got GPUs, we've got systems on chips, kind of the combination thereof, right? And this is just an onboard method. And then you've got the distributed method, where you now imagine everything's on the cloud, everything's online. I think the way to view these two paradigms is the same way that you imagine computation occurring nowadays with any type of other software. The move to the cloud is something I think that will happen for autonomous vehicles. But at the moment, the self-driving solutions that are all being implemented, it's all being done with local compute, really just because there's a need for simplicity. These people are barely getting these things to work with the algorithms right now, with the sensing right now. They're focusing on fixing those things before they're focusing on leveraging a cloud network. They want to get it working, then they're going to optimize it, right? And it's the same way that the internet transformation occurred. People wanted to build really cool software, and then they realized, okay, now that we know how to do these types of things, we can put them up in the cloud. We can leverage a distributed network. You don't need to run software locally on your computer. We can run, we can build an AWS for things that makes it so that you can actually have some sort of distributed muscle outside of your own device. And I think looking at the local processing units, I don't think they're ever going to go away, because I think these are still what you put in these cloud networks later on in the future. But people are coming up with really unique things. Google actually is working on a TPU. It's what powered their AlphaGo. And so there really is interesting stuff coming up in the hardware space still, even though people all talk about the cloud. There will eventually be an AWS for Amazon, or an AWS for AVs. That's something that's a huge opportunity. People are working on it, and it's going to happen eventually. But I think the hardware that's going to be in those server racks and those farms off somewhere, it's still going to be your GPUs, the TPUs that are now coming out that are optimized specifically for this purpose. I mean, NVIDIA released a whole deep learning platform specifically for cars, the NVIDIA Drive PX. So it really is a fast moving space. And all these information literally came out over the summer. So it is moving so lightning fast. It'll be interesting to see what happens over the next 2 years in this space, but this is something I definitely would want to keep an eye on. Actuation. So actuation, thankfully, it's a little simpler than the rest. It's basically just the field of controls and this field of electromechanical systems and the control of those types of systems. really it's the processing stages, sending data, sending commands to some type of actual mechanical system in the vehicle, whether it be like a control board, that, a bunch of circuitry that controls the engine. It's just types of control units, and these have been made in absolutely massive scales by companies like Delphi and Bosch. Big Auto has had this absolutely nailed down for the past 20 years. J1939, it's a CAN bus architecture, so it basically allows this information to travel pretty seamlessly, very quickly. Really, the highlight of this is that this is a well-studied space. This is something that people have put millions and billions of dollars in R&D into over many decades. Big Auto and all their OEMs and their suppliers really understand how this space works. It's not something that's going to be totally disrupted by like new types of startups. There's no underserved customers. The innovation in this space is going to be much more iterative. It's not affected by artificial intelligence. The incumbents are heavily positioned to dominate this, especially for the software, or especially for the hardware side of it. Manufacturers like Delphi and Bosch, especially, they're even getting into the space right now for outside of this, because they have such great expertise in this area. So really, this is I hate to say it, but this is the least interesting area of the stack, because it's something that's so heavily explored. It's very far ahead compared to the other spaces. So kind of forward looking, what's up next? What are the trends? What are we wanting to talk about? What are the big things? Well, kind of at a high level, just my general comments on each space. And, this is kind of dense and kind of thrown together. I actually wasn't going to include this initially, but I wanted to kind of make some remarks on the high level trends. The cost of sensors are just really falling through the floor. You look at Moore's law with transistors, and that's the same exact thing is occurring across solar panels right now. It's something that solar panels are becoming cheaper and cheaper. LiDAR. I mean, we looked at that MIT DARPA research project where they've got a $10 to $20 LiDAR unit that will continually to be iteratively better. There really isn't a best sensor yet. So even though this LiDAR is being iterated, we don't know what is the best, because there really isn't a ubiquitous solution out there. So that's a huge opportunity, but it also makes it difficult for people who are building on the technology, because there's nothing that they have to work off as a platform yet. Other big thing in sensing is the accuracy limits, the distance, the precision, the latency even of like spinning Velodyne LiDAR. It's got a lot of latency. But it is improving almost exponentially when kind of marginalized with or when you take the magnitude of it relative to the cost, right? These things are increasing absolutely beyond fast, year over year, massive growth. So it's a really cool space. The companies in it are going to continue to grow, and it's going to be great for really the foreseeable future. Within processing, the big question right now is really just the models, using things like SLAM, using things like GPS, neural networks. Do you mix them? How do you mix them? There is literally no best practice. There are very, very few implementations, none that have achieved scale. The book is open. There are no experts in the space. There are people who have become experts based on research, but there are no right answers, which is awesome, because it's a huge opportunity. And so local compute is, again, same type of thing. It's the only implementation that's been used. People are going to slowly transition towards the cloud, distributed networks, the same way as software. They want to leverage that. I think that's something that cannot be understated, that the opportunity of cloud networks for self-driving vehicles and the artificial intelligence kind of stored within is a beyond monumentous, massive, any type of opportunity, just the biggest. Can't even describe it. So one of the other really interesting things for processing is people always talk about vehicle-to-vehicle communication, vehicle-to-infrastructure communication. I largely almost don't talk about it because it's something that I can't imagine being reliable without full market adoption. I think that's why I always kind of push really hard on artificial intelligence, is that I think it's necessary to have artificial intelligence. And if you have, generalized intelligence inside the vehicle that's able to understand and navigate on its own, vehicle-to-vehicle communication, vehicle-to-infrastructure communication, not necessary at this point in time. It would be great for improving speeds, for improving accuracy, for just improving like safety, things like that. But at this time, it's something that we'll have to kind of almost follow as a lagging trend, in my opinion. That's something I'd love to talk about, though. Actuation controls, mission critical safety is huge. this is actuation controls is not like a limiting factor, but safety needs to be investigated heavily. Six Sigma, one error in every 2 point something million. I can't remember the exact number, but that's way too high of an error for people who are driving on the road every single day. So the incumbents are positioned well in this space, but really the safety and security has not been investigated thoroughly. It will emerge as a space larger on that's going to really, really come out with some cool companies, I'm sure, in the area, but nothing as of yet. So my big three takeaways, these are kind of my own personal thoughts, and kind of this is my my editorial of it all, is that when we're talking about actually the business models and the businesses that are going to be delivering these types of things, the data network effects for AI systems are the sole most important factor to long-term success. So I will reiterate, kind of what I think this means is that as the self-driving vehicles drive more and more, having a network effect that allows you to leverage your data and create a better artificially intelligent system, that is the one most important thing. That is I wouldn't say it's the only important thing, but it is the one most important thing. And so I give a +1 to Uber and Tesla, not even like a +1, like a plus like N, just boundless. It's insane how important that is. And I think the reason why is just because it just provides defensibility. And kind of like being able to bridge the gap from having no implementation or having an implementation to having a scaled business model. That's something we can talk about more, but that really, I think that is super important, and it's something that I could talk about for a whole hour and make a whole other presentation on. Second big point, LiDAR and GPU companies. They're going to become important OEMs. They're going to become providers for manufacturers. They're going to become manufacturers providing services to big auto manufacturers, right? They're the only non-commodity hardware that enables autonomous vehicles. So you look at the vehicle itself. How many vehicle companies are there that make vehicles that are capable of driving? There are a lot. But how many LiDAR companies, how many GPU companies are there out there that are capable of building these types of systems? These are the really key hardware pieces that go into enabling autonomous vehicles. They're going to become absolutely massive companies, more so than they are now. And that's why I'm super long on NVIDIA. I just think they're crushing it. I think they're doing great work in this space. They're going to become the muscle of artificial intelligence. They're not going to be just a gaming company. And the same goes for LiDAR. It's going to be a race to the bottom in cost. It's going to be a race to the top in performance. It's going to be awesome. So then my big third thought is just inherently the difficult problems are software related. What's hard about autonomous vehicles is not the vehicle, right? Big Auto is not positioned to win at software because the hard problems are software, and Big Auto has never done software well. I mean, you look at a lot of big automotive companies and they can't even make a great interface in the dash. Like how do you expect a lot of those individuals then and the teams that they're working with to be able to crank out some of the most forward-thinking research and the most innovative and scalable solutions in software? In this case, I defer to startups with ex-researchers, people that are coming out of artificial intelligence research labs, people that are coming out of massive companies like Google and Facebook, where they've scaled systems, software systems specifically. Scaling a manufacturing system does not help you win at software. And I think that's what Big Auto has done well for decades, and they're not positioned to win at that aspect of it. So I think really the implications of that, kind of understand those on your own. But those are my really big opinions on that kind of battle between Big Auto and startups. I threw this slide in there just for fun because I thought it was really funny, actually. I had it in kind of my appendix on here, but I actually went and visited Auto this past summer when I was working out in San Francisco. And I went and visited them before all the news of the acquisition, and I had them on my list of like really cool companies I thought was in space. Clearly, I'm making some bets right because Uber acquired them for apparently something about 1% to 2% of their equity. Comes out to about like $600 million. Pretty insane. So another really cool company, Zoox. A lot of their team is totally fantastic. They kind of have Jesse Levinson. There's news of kind of Sebastian Thrun working in and about with them, things like that. They had a $200 million fundraise, and they don't even have a real landing page up. It's just their logo. So who knows what's happening there? Can't wait. Comma.ai, probably the most exciting on here, just in terms of what they provided, the technology. They're really wanting to unbundle autonomy and decouple it from the vehicle and make it a service, make it something they can sell. the same way Cruise did, maybe with a deep learning approach though, right? They do it with cameras. They're looking at some other stuff with LiDAR potentially, but the papers they're writing, the work they're doing is fascinating. The team is interesting to say. So it's really cool. Check them out. Drive That AI came out of stealth recently. They're a software company for AVs. Not much info, but rockstar team coming out of research groups at Stanford, at Johns Hopkins, all over the place. Deep background, and that's what we're looking for, right? Peloton technology, it's an immediate use case for semi-autonomy, like, really not totally autonomous systems, but, giving a little bit more autonomy, maybe like tier 2 to semis and helping them platoon. Something cool that I noticed was under their investors, and shout out to Niraj for this. He pointed this out actually to me, that they have really strategic investors, which is a great sign. UPS, the United States or the United Postal Service, their venture arm is a big time backer as a part of the last round that Peloton raised. Clearly a great sign for Peloton. It shows that they kind of have that product, maybe not a product market fit, but their mission and really aligns with the market they're targeting. So really cool for them. Nutonomy has released a lot of information, kind of positioning their product in Singapore, releasing. It's a great team. Something that's not listed on here is Uber. I think I didn't even want to put it on here because that just draws so much kind of conversation from that. But really, I think Uber is unbelievably well positioned. I think Tesla's unbelievably well positioned. I was actually looking at smaller companies when I was making this list, so I didn't include them. But they're absolutely people you should be paying attention to right now for the next 2 years. It's going to be crazy to watch. Then kind of transition into the leasing model potentially, things like that. I'd love to talk about it more, and I think I'm going to actually maybe create a follow-up presentation, kind of giving some feedback upon this one once we see what people have to think. But really, that's kind of all I've got. I really appreciate everyone joining in, everyone who came online. I want to open up to questions, and I'm going to check the chat out and see. But I really think autonomous vehicles have the chance to be the most important technology, physical technology, to come into existence in the 21st century thus far. Maybe just as much as the smartphone, and that's a huge statement. I mean, the smartphone's, I think, probably the most important physical product ever created, and I would say that the autonomous vehicles and autonomous transportation might even have a greater democratizing effect. They might even be able to create and generate more prosperity, more wealth, equally around the world than anything else ever. And that's a huge weight to put on the shoulders of everyone out there working on it. But it's unbelievably exciting, and absolutely cannot wait until things can keep happening. Just a funny note, as I was making this presentation over the past 3 months, I continually would update things, and new information would come out, new research would come out, and I would have to rip out slides and put in brand new slides talking about actually the most cutting edge. That's how fast this space is evolving. It's something that I would recommend people to be getting into, whether it be from the perspective of artificial intelligence, whether it be from the perspective of the business models and working in the logistics and sides of that, whether it be for companies like Uber, things like Flexport. Really, just the whole space of autonomy and the whole space of transportation is something that is not going away anytime soon, and it's only going to create new opportunity and wealth on a scale that we maybe haven't seen ever, in our lifetimes, and that's for sure. So thanks to everyone who helped me out in creating the presentation. I got a lot of great feedback from people, Niraj especially. Couldn't have done it without you, man. So I'm going to take some time now to open up to questions. I'm going to head back into the Hangouts, and we'll see the Q&A. I'm going to try and add that in right now. I don't know exactly how to do that, and we're going to try and figure it out. But if you have any questions, maybe you could text me them, or you could message me them on Facebook. Let me see right here. Going into the chat, if I'm going to add some stuff in here now. feel free to drop me a line. Feel free to shoot me a message or whatever it would be, and we can kind of take some more discussion. If not, feel free to drop off. Thanks for joining. I really appreciate it. Hopefully, give me some feedback. Give me some feedback. Shoot me a message. I really appreciate you stopping by. I'll stay on the line here for another like 3-4 minutes. See if anyone's asking questions. If not, I might drop off. But if you want to take it offline, you want to shoot me a message, feel free to do so. I'd love to chat. And like I said, I am actually going to be recording this, and what I'm going to be doing is posting a video link to it on YouTube later on. So I'll put that out in like the Facebook event. I'll put it out on Twitter. If you don't find the link to it somewhere, just again message me. Reach out to me maybe on Twitter. My Twitter handle is @WileyCWJ. DM me. I can shoot you a message and we can figure it out. So cool. Any questions? Not seeing anything in the chat. Oh, actually, Niraj posted a question on the wall. So I can tackle that really fast right now. He actually asked, he asked, might have missed this, but how tough of a problem is near constant time processing on the car itself? So that's something that I kind of said maybe in a roundabout way earlier on. If we go back and look at some of the issues here with accuracy limits, distance limits, latency of data feed. Near constant time processing on the vehicle locally is still pretty hard. And largely that's due to latency of the data feed, especially with LiDAR. Most LiDAR implementations out there right now are the rotating kind, and the refresh rate of data coming in is actually limited by the speed at which the LiDAR is rotating. And so there are a lot of limits and like brick walls that people are running into in terms of processing, even locally. A lot of that's not usually around solving the matrices, solving the tensors. A lot of the matrices are pretty sparse. There are a lot of methods and SLAM methods and algorithms out there that people have for solving sparse matrices pretty well. There's a couple really good talks on that. You can look up on the Carnegie Mellon Robotics Institute. I'll actually comment back on that with some of those videos to kind of see how those work. But like I said, it ranges depending on the resolution you're looking for, the time of the refresh rates. The speed at which the car's traveling even, the faster the car's going, the harder it is to gather that data, right? So it does depend. And it's definitely still not an easy problem by any means. It's something that where a large amount of the research is actually focused is on that. Looking here now and seeing if there's any other questions, any other chats. Well, I think that might be a wrap. I appreciate everyone staying on and everyone who joined in. Thank you again for coming. Feel free to message me any questions on Facebook. I'll post, everywhere, all the different links to all the different videos. I'll post everywhere all the different, all the different types of additional resources and extra stuff. I'm actually going to put the slides up on a slide share. I got to throw in like all my citations and stuff like that before I post it on SlideShare and stuff like that. So that might take me a couple of days, but I'll ping everyone and put that out there once I've got that done and edit the video up. So thank you again for coming in, hopping on, everyone who did. I had a fantastic time doing this. It was an amazing learning experience. Hope you learned something too. I'd love to get feedback. This has been like a huge time effort, an effort for me because it was such a fantastic learning experience. So really any positive, negative criticism, any constructive criticism, anything would be totally appreciated. So thank you very much. Have a good night.